Start this lesson, 66B, with an exercise. Can you remember? It was just last lesson. Can you remember the four big properties of inverses? Please pause. See what you can remember here. Well, they were something like this. The first one. If you have a point A comma B on one graph, let's say is on the graph of F, then I like to do a lot of my math this way. I put the if and then the then. I don't know. I just throw that out there. If point AB is on the graph of F, then the point BA is on the graph of the inverse. It's like the x's and the y's kind of trade places in some sense, right? X becomes y, y becomes x. That's the big thing. That's a handy thing to think about. The x becomes the y becomes the x. Second thing, and this is kind of a corollary of the first, the domain / range of F is the range / domain of F inverse. What am I saying here? I'm saying the domain of F is the range of the inverse. And I'm also saying that the range of F is the domain of the inverse. So they switch places. And again, this is a consequence or corollary, whatever you want to say, of switching the x's and y's around. Because the domain is the set of all allowable inputs for x. And so the set of all inputs for x becomes the set of all outputs for the inverse. The domain of one becomes the range of the other, and vice versa. Okay, so that's another property. Third property, remember looking at the graph, you saw that the graphs were reflections, right? So the graphs of F and F inverse are reflections, and they were reflections across the diagonal line. Across the diagonal line. Which diagonal line? The diagonal line y equals x. Slope of 1, y-intercept of 0. That kind of diagonal line. Okay. And then the other big property was actually the big property was called the fundamental property of inverses. The big one. And it goes like this. If you plug the inverse function into the function, or if you plug the function into the inverse function, either way, the result simplifies to simply x. What goes in comes out. And this is kind of saying x becomes y, y becomes x, because you plug x into the function, and you get out a y, and then when you plug that into the other function, you get back to your x. So this is what functions do, and these are the four big properties. Okay, so again, this general concept of x and y switching places, that's huge. That's the main thing. So now what we're going to do in this lesson today is we're going to learn how to find the inverse of a function. So we're going to do it two ways, graphically, and we're going to later do it algebraically. Graphically is the fun way. I like the fun way. You get to doodle, basically. And again, so if you have the graph of a function and you want to find the inverse, you're going to use the basic idea that the x's and the y's switch. So let's look at this first graph. If you read the coordinates at this point, it looks like x is 1, y is 6. Well, the inverse then will have to have the point 6, 1. It has to, because the roles of x and y are switching. This function over here has, well, look, it has a y-intercept of 4. Well, if it has a y-intercept of 4, then the other one's going to have an x-intercept of 4. See, everything, the roles of x and y completely change. This one has an x-intercept of -2, so we expect this one to have a y-intercept of -2. Just every time x comes out of your mouth, make it a y, and you'll be talking about the inverse. Let's make that point a little bit bigger. Okay, and so we can kind of, well, maybe I'll just be official here. here's a point that, what is that? That'd be like -6, -3, which means, of course, that the inverse will have to have -3, -6. The x's and the y's just kind of trade places. And let's get this elbow point here. This looks like the point, what is that? -3, -2. And so if that elbow is at -3, -2, I want to look for -2, -3. And that's where that elbow will be. So now I can join all these things together. And doesn't that look like a nice reflection across the diagonal here? Just draw a nice 45-degree diagonal. You see that this point reflected over to this point reflected over to this point, the elbow reflected to here, this point reflected to here, and so on. It's a perfect reflection across the diagonal line. But wasn't that fun? You basically, everything that was x becomes y, and everything that was y becomes x. I invite you at this point to try these two yourself. Pause and then watch what happens when you come back. Okay. This function, this one in the middle here, seems to have a horizontal asymptote at y equals 2. So I'm going to put one at x equals 2. It's going to become vertical. Horizontal is going to have to become a vertical asymptote. But it was at y equals 2, so this must be at x equals 2. Cool. I love digging on the y-intercepts and the x-intercepts. So this will get a y-intercept at about, what would you call that, 1.5 or something, which means the inverse must have it at x equals 1.5. Let's see, the function has a x-intercept at 4. So the other must have a y-intercept at 4. Is that 4? 1, 2, 3, 4. Yep. And once you've got enough points, and having the asymptote helps a lot, and plus you have this expectation that it is supposed to look like a perfect reflection across this diagonal here. So try to imagine taking some ketchup, smearing the ketchup all along there, and then folding the paper across, right where that green dashed line is. Fold the paper and say, well, where's it going to make a mark? And it's going to make a mark something kind of like this, right? It's got to go along the asymptote, you know that. And then see what this is doing out here. This has to do out here. There's my x-intercept, there's my y-intercept, and so on. It's all reflections across the diagonal line and stuff. Now let's make it look less messy. So hopefully that's what you got on that one. This next one. So this one's got a couple points here. This looks like what? X is -2, y is 4, and then this one looks like, what is it? X equals -5, I guess. Y is 4. So if I put both of those points over here, I'd have to go 4, -2. Let's see, 1, 2, 3, 4, -2. That's this one. And then I'd also have to do 4, -5, which is like here. Okay, and then let's see what else we got here. That would be the x-intercept at about -3.5. So now I have a y-intercept at -3.5. All x's become y. All that is y becomes x. All that is x becomes y. And to try to make it look more or less the same, it's kind of a pointy-ish, parabola-ish thingish. Thinger-winger. You like that? You like that answer? It's a terrible answer. Why is that a terrible answer? We got a problem here. That's not a function. You can't say it's an inverse function if it's not a function in the first place. That's not a function. Why not? Well, it fails the vertical line test. Fails the vertical line test. Maybe I'll even write that down. Fails the vertical line test. No good. What you'll end up doing is you'll end up crossing this thing out and saying it doesn't have an inverse. Maybe I'll take that back, but it doesn't have an inverse. And so that brings us to this very important to note. There's a thing called one-to-one functions, and this is actually pretty quick to describe. So I'm gonna start by saying, well, you know that all functions have to pass a vertical line test, right? All functions pass a VLT, means vertical line test, semicolon. A one-to-one function is a special kind of function. A one-to-one function also passes a horizontal line test. Why do you want a horizontal line test? Well, that explains why this thing didn't have an inverse. See how we had these, if you draw a horizontal line here, notice the function crosses the horizontal line in 2 points. It's still a function, but it's not a one-to-one function. But the point is, these 2 points that are on this horizontal line will get reflected to this. The horizontal line has to become a vertical line, right? So these 2 points were on a horizontal line, so over here they end up on a vertical line. So that's why you need a horizontal line test. So if a function does not pass a horizontal line test, it's not going to have an inverse, and that's the key point here. Only one-to-one functions have inverses. So if you're looking at a graph, you want to kind of make sure that the graph passes the horizontal line test first. So this one here, it sure did. There's no horizontal line crossing it more than once. So it had an inverse where no vertical line would cross it more than once. This function, there's no horizontal line that crosses it more than once, which means it's inverse. There will be no vertical line that crosses it twice. Whereas this one fails the horizontal line test, so if you didn't know it already, you were soon going to find out that it fails the vertical. It's, what you think is its inverse is not really, doesn't count. It's not a function. It fails the vertical line test. It's not a function. It's a bummer. So I guess I'll leave all those smears there because we're going to change pages. So that's the thing to know, and that's about all you got to say about graphically determining functions, or inverses, I'm sorry. Let's look at algebraically determining an inverse. So, I mean, you could try, I guess you could try to make a graph of that first. If I did make a graph of that, what would I get? I would get something like, let's see now here. You have to start at -4, right? If you plug in a -4, you'll get y equals 0. And then if you plug in like a -3, you get the square root of 1 is 1. And if you plug in like a 0, you get the square root of 4 is 2, and so on. Anyway, it looks something like that. That's what that function looks like. Is it passing a horizontal line test? It sure is. So that means we can go ahead and just fearlessly try to solve for the inverse function. Now, solve for the inverse is part A. Here's how you do it. How did we do, wait a minute. How did we do this? We said the role of x and y is reversed, right? Same thing. The role of x and y is reversed. Here's what that looks like. So the first time I do this, I always write it out. So this function has a certain relationship between the x and y coordinates. It has this relationship, right? It's given by the function. The y is equal to the square root of x plus 4, semicolon. Its inverse will have this relationship. The x's and the y's will change places. So that's kind of the secret. You just take the y, make it an x. You take the x, make it a y. Well, now you solve for y. But that's basically it. So let's solve for y real quick. I got a bug in front of me. You bugger. The bug's a bugger. Now solve for y. Okay, so what I'm going to do, I'm going to basically square both sides, right? So I got an x squared over here. The square takes the square root off. Maybe I'll just change the two sides of the equation around because I want to solve for y. Oh, I'm practically there. I just got to go x squared minus 4. There's the inverse right there. Okay, that wasn't hard. Okay, let's verify now. Part B. Isn't that part B? Yeah, part B, prove your result. So we're going to prove our result. So this is that fundamental property of inverses where you have to show two things. You have to show that, well, the first thing you have to show is that if you plug the inverse into the function, it will simplify to just x. And, oh, by the way, I wasn't exactly done over here because I should have said y equals x squared minus 4 means that the inverse function is x squared minus 4. That's a nicer looking answer, ain't it? Sure. So anyway, when I go plug in the f inverse into the function here, what does that mean? It means I'm going to take this and I'm going to plug it in as the input to this. So I'm going to have the square root of, now I go grab my inverse down there and I plug it in, x squared minus 4. Okay. So that just went right there. And then I say plus 4. Okay, that's all in the square root. Now, the minus 4 and the plus 4's cancel. You've got square root of x squared, which is just x. It kind of works. Except, remember this came up in the last lecture too. We have a domain restriction here. This requires that x not be negative, right? In order to say that the square root of x squared really is x, it doesn't work if x is a negative number. Because if you take a negative 2 and you square it, that's a 4. And if you do a radical 4, you get a 2. Well, that's not what you started with. You started with a negative 2, you ended with a positive 2. So that actually, to say the square root of x squared is x doesn't work if you use a negative value of x. So I'm going to note that here it requires that x is greater than or equal to 0. And so that becomes, since that's the thing I'm plugging in, that means that this has a restriction, x must be greater than or equal to 0. Okay, just being careful here. Now, we also have to show that it works the other way. Plug the function into the inverse. Maybe put question marks here and there. Does that work? Well, so now I'm gonna go up and grab the function, which is this, the square root of x plus 4, and I'm gonna plug it in for the input there. So I would have, okay, so plug in the input, square root of, what was it? Square root of x plus 4. Make sure I do the same, right. Make sure I do it right. So square root of x plus 4, that's being plugged in there. It's being squared and then minusing 4. Now when you square a radical, out comes the x plus 4. And so guess what? You really do just get x. And so the idea that it worked both ways, as long as you take into account a domain restriction, the idea that it worked both ways means, yes, we have verified, we have proven that these are indeed inverses of each other. Now, part C. Let's talk about some domains and ranges and stuff. Back to blue. So part C. Domain of f. Well, let's go look back at f. F is this thing. What's the domain for this function? What are the acceptable inputs? What is the complete set of acceptable inputs? Well, we're talking about real valued functions for this whole rest of this course. So that means you wouldn't, if you use a negative 4 for x, that would be fine, because negative 4 plus 4 is 0, square root of 0 is 0, but you cannot use anything less than that. So there's a domain restriction here. X has to be greater than or equal to a negative 4. So I'll write it this way. It's kind of a shortcut notation. If I wanted to be real good about it, I'd write it this way. But I hope you don't mind if we just take the shortcut. So that's the domain of f. Fine. What's the range of f? We're not going to do that yet. This is part C. What we're going to do next is we're going to do the domain of the inverse. And you'll see why we're doing this in a minute. So the inverse function, well, it's right there. And this is why we had to be careful about this square root of x squared thing. Because if you just look at x squared minus 4, you might think, oh, I can plug anything in I wanted to that. It's all reals. Except it isn't. We do have this restriction here. X must be greater than or equal to 0. So, okay, x must be greater than or equal to 0. And then the range of the inverse is what? Well, the reason I held off on doing the range for the other one is because here's how you find the range. Remember, the domain of one is the range of the other. Ranges are harder to figure out. You know, a domain, you look at it and you say, well, if I can't have a square root of a negative, I can't divide by 0. Domains are easy to figure out. Ranges are like, well, I don't know. I'd have to graph it. But there's a property of inverses that says if this is the domain of the inverse, that has to be the range of the function. And you use y instead of x, but it's the same set of numbers, all numbers greater than or equal to 0. Try to make that look like a greater than. Okay, and then here, the domain here becomes the range here. Use a y instead of an x, but it's the same set of numbers. All numbers greater than or equal to -4. All numbers greater than or equal to -4. And that's how you answer that question. I always thought that was kind of fun. Actually, I might as well leave those arrows there. Okay, so let's just verify this on the graph. Remember, we drew a graph up here real quick, right? So the function has the domain of, yeah, x has to be greater than or equal to -4. We agree. And the range of this thing, well, actually, you can tell by looking at the graph. It's y is always going to be something positive. Y is always going to be, well, not negative, I guess. It's going to be 0 or more, and that's what we got for the range. Now, what would the inverse look like? Doesn't that look like a parabola? Except that it's only the right branch of a parabola. It's not the whole parabola. We're saying x has to be greater than or equal to 0. So actually the inverse, let's see, I might have mentioned, it's a parabola that got shifted down 4. So it'd be like down here, and then you'd have your parabola shape. And you know how to graph it because it has to look a lot like that thing did. But you can see where this domain restriction is actually very important. You can't say that the inverse function is a parabola. Parabolas don't have inverses. It would fail a horizontal line test, blah, 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 blah. Okay. So, yeah, kind of a lot going on there. Let's do this again for good practice here. This will be a slightly fancier function. I find it's good to practice with our rational functions. So here's a rational function. It's a ratio of two polynomials. Let's solve for the inverse. Okay. So remember, what you do is you switch the x's and y's around. This is kind of like y. So we're going to call it x now. And then there's the 5x. We're going to call that 5y. Over 3x, we're going to call that 3y. So solving for y is the trick here. So I'm going to do the old multiply both sides by 3y trick, so that I have on the left side, if I put the letters in order, it's 3xy, and on the right side, of course, that canceled off. I'll have a 2 minus 5y. Now that's going to look a little weird, I suppose, but we're trying to solve for y. So you want to get your y terms all together on the left side. That's how you get started anyway. So I'm going to add the plus 5y on both sides. Yep, that's what I'm going to do. That is my plan. Okay, so I'll have a 3xy, and then I'll add the 5y on the left, and then the 2, and when I add the 5y on the right, it cancels the negative 5y. Okay, cool. Now, how am I supposed to get y by itself? It's in two places, right? It's here, it's here. How am I supposed to get it by itself? Well, remember that idea of factoring out a common factor? Y is common to both. Undistributed, so to speak. Cool. There we go. That works. And now all you guys do is divide both sides by that parentheses thing. Cool. We did it. We ended up someplace nice. And so now we can call this the inverse function. 2 over a 3x plus 5 like this. That would be, or should be, the inverse. That was part A. Part B, prove your result. Okay, this is where you have to do the old plug the function into the inverse and vice versa trick. Let's plug the inverse into the function and see what we get. It's supposed to equal x, does it? Well, let's see. Okay, I'm plugging this. This has got to get plugged in for the x there and there. What's that look like? Well, I'd have a 2 minus a 5 times, take that and make it the input. 2 over 3x plus 5. Okay, and on the bottom I'd have a 3 times and make that the input. 2 over 3x plus 5. Okay, well, remember the good news is it's supposed to simplify to just x. So it looks like a mess now, but it should get less horrendous, not more. Let's hope. Okay, so the first thing I'm going to do is I'm going to say, okay, that 2 is like a 2 over 1. And we got fractions going on. We're going to need a common denominator of 3x plus 5. So right now, multiply the top and bottom by a 3x plus 5. Okay. And then it's minus, and then that 5 is like a 5 over 1, where we have a 2 on top. Well, we have a 2 over a 3x plus 5. Okay, cool. Underneath, this is like a 3 over a 1, multiplying a 2 over 3x plus 5. Okay, so that's just setting up my fractions so I can add and subtract and stuff. Now, since I have a common denominator here, that means I can combine across the top like this. So what have I got here? I've got a 2 times a 3x plus 5 minus a, 5 times 2 is 10. I'll just say that right now. So that's all over the 3x plus 5. And then on the bottom, we've just got 3 times 2 is 6. All over the 3x plus 5. Okay, cool. Now we can cancel these since they're on the bottom of both. And so this is looking pretty good already. So I got, if I distribute here, I got a 6x plus 10 minus 10. That's all that's left up top. I got a 6 on the bottom. Oh, look at this. This is a 6x over 6, which is an x. It worked. Awesome. But don't forget, we have to do it both ways. So does plugging the function into the inverse also reduce to just x? Well, I hope so. So I got to take this, and I got to plug it in down there. So that's going to be a 2 over a 3 times the, plug it in, 2 minus 5x over 3x. Did I copy that right? 2 minus 5x over 3x, good. And then I got this plus 5 sitting here. Okay, cool. Okay, cool. So, well, the top is pretty simple. It's just a 2. What's going on the bottom here? Well, that's like a 3 over 1. That's like a 5 over 1. So, why don't I just say it right here? I'm going to have to multiply that by a 3x over a 3x, right? To make sure I get 3x's for common denominators. So then I'm going to be able to, since they have a common denominator, I can combine across the top. That'll look like this. 3 times a 2 minus a 5x plus a 5 times a 3x. That's all over my common denominator of 3x. Okay. So what do we got? We got 2 over. This will be, if I distribute, I'll have a 6 minus a 15x plus a 15x from over there. That's all over a 3x. 2 on top. Notice the 15x's are canceling, so this is just a 6 over a 3x. So remember how you do this. It's 2 divided by the 6 over 3x, which means it's 2 times the reciprocal, 3x over 6. And you can kind of see a lot of canceling here. So the 2 goes into the 6 3 times, and then the 3 goes into 3 1 times. You get x. Yeah, it worked. It worked both ways. We have verified, we have actually proven that these two things are inverse. They're a pair of inverse functions. Let's go back to blue now. The last two parts are domain and range, right? Okay. Domain of f is what? Basically, you can't use x equals 0. And I'll start answering question C now. The domain of the inverse, looking at this one, x cannot be, let's see, that would have to be a negative 5/3. Put a negative 5/3 in there, you'll have a 0 denominator. That's no good. So the range of f is this, except you use a y. Y cannot equal negative 5/3. And when I write this, what I mean is y is every other real number except negative 5/3. Anyway, as far as the range of the inverse goes, you grab that. The domain of one is the range of the other. That says all numbers that are not equal to 0. So the range will be all numbers that are not equal to 0. Use a y instead of an x. But there. That's pretty good. We're rocking and rolling. Let's see, is there anything else I wanted to mention here? I don't think so. That's you know what? I might throw this in just because I've been seeing a lot of people. They seem to really like this interval notation. So, P.S. If you want to use interval notation, then you got to use it right. Doesn't count if you write it wrong. You got to write it right. Write it right. Yeah, that's it. So what does x not equal 0 mean? First of all, I'm already taking a shortcut. I should be saying the set of all real numbers x with the condition that x does not equal to 0. That's what I should be saying. What does that look like on the number line? It looks like this. Number line goes from negative infinity to infinity. You'd have a big hole here at x equals 0. How do you write that? You would say from negative infinity up to 0, union symbol, 0 up to infinity. The key thing to note, it's like I'm taking the number line and I'm putting it down here. So I go from negative infinity to 0 first, in that order, from negative infinity to 0. It's always left to right. The union symbol says, well, these two things are joined together. These two sets are joined into a single set. And then you get 0 to infinity over here. Okay, again, you have to go from in order, from smallest to largest, in the same order as the number line. It's very important to do that. So, what else we got here? That's how you would write x not equal to 0. How would you want to write y not equal to negative 5/3? Which, again, what I should be saying is the set of all real numbers y with the condition that you don't use negative 5/3. That's the way I should say it. What does that look like on a number line? Well, negative infinity is over here, positive infinity is over here, and the negative 5/3 is, somewhere in the middle. And we're not supposed to use it, so there's like a big hole. So you are able to use these values, and you are able to use these values. So, taking this information, which is a nice pictograph, it gives you all the information you need, really, but you can sort of type it, I guess, by saying, well, go from negative infinity up to negative 5/3, round bracket, because we do not include negative 5/3. But then we're going to glue that set to this other set, which starts on the other side of negative 5/3, so to speak, and goes to positive infinity. Again, go in the same order as the number line. You got to do that. Just try to think of this as sort of like taking the picture, and I don't know, to me it seems natural. It's like if that's the picture, then it makes me want to write it that way. Just makes me want to. Okay, cool. Let me get some of this green stuff out of here. So I guess I'll end with that. So cool, that finishes section 66 on inverse functions. I'm going to change gears next time.